Sequential logic is our next topic as we study digital electronics. In this short video, we'll take a high-level overview exploring what the technology can do. Then we'll step back and we'll look at some of the building blocks, such as flip-flops. As we start, I'd like you to consider a parallel bus formed from inputs A, B, C, and D. We'll let A be the least significant bit, and we'll let D be the most significant bit. As we move in time, A will have a signal that looks like this. Just a square wave, nothing very exciting there. B is also a square wave, but it has a frequency 1/2 that of A. C is another square wave, half the frequency of B, and we'll show just a little bit of D, yet another square wave with half the frequency of C. In this example, we use the word bus, which implies that the wires are somehow working together to provide a common signal. In this first signaling event, right here, A is 0, B is 0, C is 0, and D is 0. I should have mentioned that this is a function of time. In the second slot, we see A is 1, all others are 0. In the third slot, A is 0, B is 1, and so on. So we move from 0, 0, 0, 0 to 0, 0, 0, 1 to 0, 0, 1, 0, and I think you can see the pattern there. What we've done is we've counted from 0 up to 1, 1, 1, 0, which is binary 7. I'll leave it up to you to fill in the rest of this chart so that we can go all the way from 0 up to hex F. Here's a real-world example of this bus. We start with what's called an up counter. With a 4-bit bus, we'll send that to a decoder, which will have multiple output wires, which can then be used to drive a 7-segment display. Back to this vector, D down to A, we see that right here. The up counter in 4-bit binary will send a count to the decoder, which will then drive the 7-segment display. So it could run from 0 all the way up to hex F. So we would say these 4 wires count from 0, 0, 0, 0 to 1, 1, 1, 1. But maybe you don't want to count from 0 to F. You could certainly modify this up counter to count from 0, 0, 0, 0, base 2, to 1, 0, 0, 1, base 2, which is to say to go from 0 to 9. In fact, you could make the up counter go to any modulus you desire. In fact, that's what it's called. It's called a mod M counter. Maybe you don't want it to count up. You could modify the circuit so that it counts down. Whatever we decide to do, we have to remember this. The counter is a sequential circuit. Where the next output is dependent on the present output. There's no surprise there. After all, if we want to get to the number 5, we first have to recognize that we're at the number 4. And to do that, we need memory. We need a structure that looks something like this. In the center, we have that combinational logic that we've been studying. The machine has one or more outputs and may have several inputs. To this, we add something new. We add memory. The state registers are memory. There's a few terms associated with this memory. On the input side, we have the word next. And on the output side, we have the word present. Those are the same words we saw up here. The counter is a sequential circuit where the next output is dependent on the present output. So if the memory is currently holding the value of 4, if it's an up counter, the next value will be 5. Know that a clock signal is typically associated with these state registers. This clock signal could be thought of as a go command. When that clock ticks, the next value becomes the present value. So what was a 4 becomes a 5, and our next value will be 6. So the next time the clock says go, the numbers will change again. Anyway, we're getting ahead of ourselves. We're going to call this structure a short-term objective. Stated another way, it is the main topic for exam number 3. For our purposes today, remember this: there is memory associated with this finite state machine. It is the memory that differentiates combinational logic from the sequential logic. With that said, we're going to step back and take a look at memory. The simplest memory circuit starts with a NOR gate, with the truth table that has F true if and only if B naught A naught. A set reset circuit can be formed using 2 NOR gates. We'll designate this the set input, the reset input, the Q output, and the Q naught output. Let's define the initial conditions as set at 0, reset at 0. Unfortunately, when this circuit starts, we do not know what value Q will take on. It could be a 0 or a 1. In fact, Q and Q naught could oscillate back and forth because of this feedback. But the good news is it will eventually settle into one value. For this discussion, we'll assume that Q naught has taken the value of 1 and Q has taken the value of 0. Looking at the truth table for this gate, when there is a 0 and a 0 in, there will be a 1 out, so that appears good. If we look at the truth table for this gate, we have a 1 in and a 0 in, giving us a 0 out. So this circuit appears to be stable at this point. Suppose we were to assert R as 1. That would give us a value of 1, 1 going into this gate, which is this piece right here on the truth table. Nothing happens. Suppose instead we were to assert set. That would give us a 1 and a 0 going into this gate, which is this point here on the truth table. meaning this output would go to 0. That 0 on Q0 is fed back to the lower NOR gate, which gives us 0 and 0 as an input. That's the first line in the truth table, which means this goes to a 1. Of course, Q is now fed back to this input, which gives us a 1, 1 in the truth table, which is a 0 out. So we've reached a stable state again. If that set is now released, we have a 0, 1 going into the upper gate, which is this. The output stays at 0. Which is fine, but it's getting a little cumbersome with all these 1s and 0s. So we'll go back to the original setup, and then we'll draw a picture which will help us explain what's going on. There are 2 states for this system. There's 1 state and 2 states. Let's call them state 0 and state 1. If you rewind the video, one of the first things we said is that we are going to assert the reset line. And I believe nothing happened because that gave us a 1 and a 1, which gives us 0 in the truth table. On this state diagram, what we just did is a line that looks like this. If R is equal to 1 while you're in state 0, you don't do anything. You just come right back to state 0. However, if you're in state 0 and you assert the set line, so if S is equal to 1, you transition into the S1 state. We know the machine is in the S1 state when Q is equal to 1. Likewise, we know we're in the S0 state when Q is equal to 0. Moving back to the S1 state, if the set line is asserted again, nothing happens. The machine stays in the S1 state. But if the reset line is asserted, it moves to the S0 state. This is a memory circuit. It has 2 states. The memory can hold a 0 or a 1. This memory will stay in that state, which is to say it will hold that bit until a very specific condition occurs. In this example, those conditions are described by the lines. If in state 0 and S equals 1, go to state 1. If in state 1 and reset equals 1, go to state 0. There is one caveat to all this, and that is don't assert S and R at the same time. That would lead to what we call undefined behavior, which is another way of saying we have no idea what the circuit will do when you assert both S and R. At this point, I would ask you to open your textbook and find the section that introduces this circuit. As you read the text, the author is going to describe a series of circuits with increasing complexity, leading up to something called the transparent data latch, which is represented as a block with inputs D and C and outputs Q and Q0. The operation of this transparent latch is defined by a few rules. The first rule tells us that Q is assigned the value of D while C is true. The operation of the circuit is suggested by the name. It's transparent. If C is high, D and Q are connected together. The circuit is transparent because whatever is on D will be on Q. And of course, there will be an inverter here to give us Q naught. Of course, if it's transparent, there must be a condition where it is not transparent. That condition is defined when C is set to 0. Q holds whatever the last value was. Let's see if we can make some sense of this using a timing diagram. Here's input D, input C, output Q, and output Q naught. For initial conditions, let Q be 0. Q naught, of course, will be 1. C is 0, and D is 0. Suppose D transitions to true, like so. Nothing will happen until C is asserted. It's C that makes the latch transparent. At that moment in time, Q will immediately become what D is, so Q will go high and Q naught will go low. While D is high, C can do something like this and it will make no difference. Q will remain high. If D returns to 0 at this point here, nothing happens. And the reason nothing happens is because that point occurs while C is low. That was one of our rules. Q would hold the last value of D when C is low. In fact, nothing will happen until the next time C goes high, at which point Q immediately goes to 0 and Q naught goes to 1. We can see the rest of the behavior by exploring what happens when C is asserted and D changes. Remember that this is a transparent latch, so as long as C is asserted, Q is going to follow exactly what D does. And of course, Q naught does the opposite. Moving on, the next memory circuit is the edge-triggered flip-flop, which will be very important to us as we move forward into the finite state machine. The D flip-flop has a block that looks like this, has a D input, Q output, and a Q naught. It has one more input, and this is something we haven't dealt with before. This is an edge-sensitive input. This is definitely not the same as our transparent latch. Here, you'll remember that C was level sensitive, while C is true, Q will be assigned a value of D, and let's not forget the inverter here to take care of Q naught. In the edge-triggered flip-flop, we're not concerned about levels. We are concerned about the edge. In this case, a rising edge. A timing diagram can be used to illustrate this operation. Suppose we have clock. We'll let that be a square wave. Input D. What values will Q take on? If we assume a starting condition of 0, we have to ask what happens on each rising edge of clock. There's a rising edge. There's a rising edge. So these are the only places that the circuit can possibly change. On this first rising edge, we see that D is low, so Q will stay low. On this rising edge, D is low, so Q stays low. Here's another rising edge. Looks like Q is going to keep staying low. At this point, D is high, which means Q will go high, and it will stay high until this point here, where D is once again 0 on the rising edge of clock. Q goes to 0 and stays at 0 until this point here, where it goes high. And of course, Q naught takes on the opposite value of Q. Here's a simple circuit using the D flip-flop. In this simple circuit, we'll connect Q naught back to D. And we'll let this be clock. Let this be the clock signal. And let Q naught start at a value of 0, which will be applied to the D input. On the rising edge of clock, Q naught will take on the opposite value of D, which means that Q naught will go high, which is fed back to D. Nothing else will happen until the next rising edge of clock, at which point Q naught will take on the opposite value of D. Continuing on with that thought process, you'll see that this circuit has effectively divided the frequency by 2. The Q output toggles on the rising edge of clock, which effectively divides the clock by a factor of 2. As we close this discussion, I would encourage you to focus in on this edge-triggered data flip-flop, because it is the heart of the finite state machine. It is the heart of our short-term objective and something that will certainly be on exam number 3.